An atom usually exists in its ground state. This is the lowest energy state of an atom. When an atom absorbs energy, whether through light or heat, for example, it enters what is known as an excited state. It is this process of an atom absorbing energy that is known, quite aptly, as atomic absorption. So how does atomic absorption work? Atoms absorb energy through allowing an electron to be promoted to a higher energy level. Different shells around the nucleus of an atom have different, distinct energy levels. The first or innermost shell has the lowest energy level, and the valence or outermost shell of an atom has the highest energy level. Therefore, an electron is promoted to a more distant electron shell when it reaches a higher energy level. However, we must remember that the energy level of an electron shell is fixed, and electrons cannot exist between shells. Therefore, to be promoted to a higher electron shell, electrons are required to absorb the precise amount of energy needed to go from their current shell to a higher shell. That amount of energy is equivalent to the difference in energy between the higher energy shell the electron would move to and the lower energy shell it currently occupies. Also note that an electron can be promoted more than one energy level at one time as long as it has the exact amount of energy required to reach that higher energy level, and that is still the difference in energy between the level it currently occupies and the level it is being promoted to. So how does an electron actually absorb energy? They absorb electromagnetic energy in the form of photons. Photons are essentially tiny packets of electromagnetic radiation, EMR. They are massless but contain a fixed amount of energy. Photons with shorter wavelengths carry higher amounts of energy than those with longer wavelengths. Electrons only absorb photons equivalent to the amount of energy required to be promoted to a higher energy level. A photon cannot be trimmed or split to fit, and it cannot be only partially absorbed. A photon won't even interact with an atom in this circumstance if it does not match the energy level required for the atom to be promoted to a more distant electron shell. Then we have something called absorption spectroscopy. Absorption spectroscopy specifically focuses on the spectra produced when matter interacts with electromagnetic radiation, in this context, through absorption. Spectra is the plural of spectrum, which is just a visual representation, commonly in the form of a chart or graph, which depicts EMR intensity across a range of wavelengths. Although we can study other forms of EMR through spectroscopy, one type we often use for spectroscopy is the continuous spectrum of visible light. This is the portion of the electromagnetic spectrum which can be seen by the human eye. The continuous spectrum contains all wavelengths of visible light. The energy levels and differences in energy levels between different electron shells differ between elements. These energy levels are distinct to different types of atoms. For instance, the difference in energy level between the first and second shell of a mercury atom is the same across all mercury atoms, but it is different to that of a nitrogen atom. Therefore, different types of atoms will have to absorb different amounts of energy to match their energy levels. These amounts of energy equate to specific wavelengths of light, remembering that photons with longer wavelengths carry less energy than those with shorter wavelengths. The shortest wavelengths of visible light appear purple, while the longest wavelengths appear red. Due to this, we can identify an element by the wavelengths of light it absorbs. The electrons of atoms and molecules will absorb photons from the continuous spectrum when visible light passes through a gas. Specific wavelengths of light will be absorbed, while others pass through. Thus, when we collect the resulting light which passes through the gas, specific wavelengths will be missing. If we separate the distinct component wavelengths, we can produce an atomic absorption spectrum. In the places where specific wavelengths are missing, dark lines will exist, because there was no light collected there. Since different elements absorb different wavelengths of light, these dark lines will consistently appear in different distinct locations for each element. We can thus use these atomic absorption spectrums to identify an element. Please like and subscribe if you found this video helpful, and best of luck with the rest of your chemistry studies.